Well, thank you all so much for joining and coming to what's the first of 6 lectures I'm putting together. So I'm gonna talk about probing quantum materials with light. And in this first lecture, I want to introduce some important material science and solid state physics concepts that I think are important to the underlying understanding of a lot of the subsequent material. So briefly, let me introduce myself. My name's Arthur McClelland. I got my Associates of Arts degree from Simon's Rock College of Bard in 1999. Simon's Rock is a small liberal arts school out in the Berkshires, Massachusetts. I then decided I wanted an engineering degree, so I went to the University of Pittsburgh. I got a bachelor's of philosophy and engineering physics. The engineering physics program at Pittsburgh at that time was basically a triple major of electrical engineering, material science, and engineering and physics. I basically couldn't decide what I wanted to major in, so I majored in everything. And then the dot-com bubble burst and there were no jobs, so I went to grad school. I went to the University of Michigan. I was in the applied physics program at the University of Michigan. I picked up a master's of science degree in electrical engineering and a doctor of philosophy in applied physics while I was there. Then the great financial crisis hit just as I graduated from my PhD. So I went and got a postdoc at Northeastern. So I was a postdoc at Northeastern for 1.5 years. And then I eventually burned out of overnights in lab and landed a job that I currently have at the Center for Nanoscale Systems, where I'm currently a principal scientist. I've been at CNS since 2011. And I largely run the optical spectroscopy, optical characterization lab. So I've had about 9 years of experience at CNS characterizing quantum materials as people bring them to me. CNS is an open shared use facility. I have about 500 users coming through my lab every year, so I see a wide variety of materials. And I wanted to share some of the background information that I picked up through my meandering through academics for a long time and some of the practical things I've learned actually characterizing quantum materials. So that's the goal of this lecture series. So what am I calling a quantum material? I'm really calling a quantum material, it's a material which displays properties that we can only explain using quantum mechanics. So quantum effects are mainly seen in electronic properties of materials. I'm going to leave aside magnetic properties of materials. Just I have to draw the line somewhere. I can't talk about everything. So I'm going to confine these lectures largely to the electronic properties of materials and how quantum effects appear in those and how they can be used for different things. So there are lots of different material properties. You can have mechanical material properties, tension, compression. Those are all classical, so we're not going to worry about tension, compression, things like that. We do see quantum materials in a variety of places. This is a picture of a magnetic resonance imaging machine. The magnet for it is actually a superconducting electromagnet. It sends out pulses. The pulses flip the spins, the unpaired spins in the patient's brain, and that generates the image. So it's very quantum mechanical on how you get an MRI. And there are quantum materials in consumer products like TVs. This particular one advertises having quantum dots to make all the colors. So hopefully we'll get to the point where we can understand how these quantum phenomena are being used and showing themselves in these types of things. So a quick outline, we're going to start at the beginning and sort of build up from the atomic elements, and then we'll put them together in crystals, and then we'll go back to electrons and talk about how we go from wave functions to band gaps, and then start with some ideas about basic building blocks to make an actual device in the end. So at the end of the lectures, hopefully we have some background on how to go from first principles up to actually generating a useful quantum materials device. So what do we have to work with when we're trying to make a quantum material? Well, all the elements known in the universe are arranged neatly in the periodic table. I think this one goes through 118 elements. Some of them are not stable for a long period of time. Some of them are radioactive. So we'll round it off to 100. So you have about 100 building blocks to work with. What do these building blocks look like? Well, if we take a picture of the atom, in very simplistic terms, we have a nuclear core, which has protons and neutrons, and we have an electron cloud around the nucleus. The protons have a positive charge, the electrons have a negative charge, and the nucleus is massively heavy compared to the electrons. But of course, all these pictures are overly simplistic. The electronic orbitals are not just circles. That would be the s orbitals. There are also p orbitals and d orbitals and f orbitals. And these orbitals really should be thought of as probability clouds for the locations of the electrons. And we'll come back to that a little bit later. But just keep in mind that the orbitals can go in different directions, and the different directions can be important in terms of the properties we see in a material. So let's start really basically. So back to the physics Gedanken experiments. Let's imagine we have a box and we start putting electrons in. What's going to happen as we put the electrons in? Well, we can model them as a classical gas. They bounce around at random. This was in fact how physicists started to try to understand solids and electrical properties of solids. Around the turn of the 20th century, Paul Drude proposed the Drude model, which is still widely used. You'll see papers saying, I invoke the Drude model for the rest of the paper. No one ever goes back and explains what the Drude model is, so I'm going to take a moment to try to explain that. So the Drude model is using classical gas theory. You're modeling all the electrons like a classical gas bouncing around in a box, and every electron is independent from each other. Now, ideally, we'd want to calculate the interaction between one electron and every other electron in the solid. A solid material has on the order of 10 to the 23 atoms per cubic centimeter. Each atom can have multiple electrons. That ends up being computationally just impossible very, very quickly. So what the Drude model does is it assumes that the effects of everything can be modeled as an average potential that's created by the ensemble of the electrons. So on average, there's some electric field that the single electron feels, and this average electric field, this average potential is generated by the ensemble of all the other electrons. It assumes that the conduction is entirely by electrons. We'll see a little bit later, the conduction can also be by holes, but we'll get to that in good time. The model assumes that the sample forms this flat bottom potential well within which electrons are free to move. We'll start with that model a little later, and then we'll quickly move to sort of more realistic models. And then it assumes that the electrons are all distinguishable. They take up negligible volume. They have this random motion. They have perfectly elastic interactions, and they have some sort of average energy. So it's a great starting point, but it fails, which was one of the motivations for formulating quantum mechanics. So the Drude model fails to predict some of the experimental properties of materials. It does a reasonable job on some, it fails on others. And the biggest issue with the model was it uses classical Maxwell-Boltzmann statistics. So in Maxwell-Boltzmann statistics, we have the probability of an electron being found in a specific energy level. At absolute zero, all the electrons will be found at the lowest energy level at zero. And then as we heat the system up, we get an exponential tail as the electrons get more and more energy from thermal sources. The problem with this, and now we need to veer just a little bit into particle physics. I'm going to not start to explain the standard model or anything, that's beyond the scope of this, but we need to know what fermions and bosons are. So electrons and protons are a type of particle that are known as fermions. Fermions have half odd integer spin, so they have spin 1/2, 3/2, etc. Electrons are usually thought to have spin 1/2 and minus 1/2. We'll go into what spin is, how we know it exists next week when we talk about the experiments that led to the formulation of quantum mechanics. But for now, just accept that there are fermions and they have half spin, half integer spins. And there's a requirement that only one fermion can occupy any given quantum state. So this is commonly known as the Pauli exclusion principle. It has to do with the wave function needs to be antisymmetric, but that's beyond the scope of this lecture. So for now, just accept that electrons are a class of particles known as fermions, and each one needs to be in a distinct quantum state. And fermions obey not Maxwell-Boltzmann statistics, but Fermi-Dirac statistics. And I'll give a model of what Fermi-Dirac statistics means in the next couple slides. Photons, on the other hand, are a type of particle known as a boson. So bosons have integer spin, 0, 1, 2, etc. And there's no restrictions on how many bosons can be in a given quantum state. And bosons obey Bose-Einstein statistics. I'm not going to go into Bose-Einstein statistics in this talk. It's not important for what I'm trying to get through in this talk. But I wanted to have the comparison and contrast, the compare and contrast between fermions and bosons. So bosons can all be in the same state. All the photons can be in the same state, and this is how we end up with a laser. A laser, all the photons are in exactly the same state, and that's why it lasers. All right. So we'll go back to our Gedanken experiment. And imagine we have a material, and we've taken out all the electrons. And for the moment, I'll ask you to accept that the electrons have discrete energy levels. We talked briefly already about the electrons have different orbitals. We'll mathematically prove why they have discrete energy levels a little later in this talk. But for now, just accept that we have this box, and we're going to put electrons in, and there's discrete energy levels. So we put in one electron, and the little arrows are supposed to denote the spin. So we put in one electron, it has a spin up. It goes to the lowest energy state. We add a second electron. We remember the Pauli exclusion principle. It has to have a spin down, and then it's going to also go to the lowest energy state. When we add the third electron, it is forbidden to go to that lowest energy state and can only go to the next highest state. And as we continue to add electrons, we fill up the energy levels from the bottom, and we can only have 2 electrons per energy level, spin up and spin down. And we can eventually build up to a full model of a material. So we fill to a certain level. This level ends up being called the Fermi level. This is where the electron population is. The Fermi energy is the level from 0 to the Fermi level. And then we'll talk about this more next week, but the work function is the amount of energy it would take to pull an electron all the way out of the metal. So how much energy do we need to yank this electron and take it all the way out of the material? That's what's called the work function. All right, so we've seen how we systematically, what happens systematically as we add electrons one at a time. So how does this apply to the Fermi-Dirac statistics? So at absolute 0, we have all the states filled up to the Fermi level. So all these states are filled up to the Fermi level, and then there's nothing in the higher states. All the states are filled up to the Fermi level, and then nothing. If we start adding thermal energy at a finite temperature, we add thermal energy, an electron will be excited up, but it has to be the electron from the top. It can't be the electron from the bottom because there's nowhere for it to go. It can't, this electron that's in the ground bottom, the lowest energy state, can't go to the next highest state because that's still occupied. So this is denoted here as in just the electrons near the Fermi energy start to move up to higher energy levels. And as we move up in temperature, again, it's still just these electrons at the higher energy levels that get to move up. The electrons in the lowest energy levels are still stuck. This lowest level is still always full. So it's a different statistical shape of the population of the energy levels, the density of states. And Sommerfeld included this onto the Drude model, basically replaced the Maxwell-Boltzmann statistics with the Fermi-Dirac statistics, so it captures the behavior of electrons, thus including quantum mechanics, and actually made the Drude-Sommerfeld model work fairly well. All right, so already we see quantum mechanics needs to be included to describe materials. All right. So we focused on the electrons. Remember, our atoms were a positive core and this negative C around it. Let's think about how we're going to put together the positive cores. How do we put these elements together to make a quantum material? So we're going to consider crystalline solids. Most of the materials that I think of as quantum materials are crystalline solids. A crystal here is a periodic arrangement of atoms. Similar to the way the boys building the blocks, we're going to systematically put together all the atoms in a certain order. The crystal is going to be this array of positively charged nuclear cores and this sea of electrons. And we're going to take a couple minutes to discuss how we can arrange these positively charged cores in physical space. So material scientists think of crystal structure as two parts, as the lattice plus the basis. So here is a cartoon of a simple cubic lattice. If we split that out, the lattice is simple cubic, and the basis in this case are the red dots. The basis doesn't have to be a single atom, it can be multiple atoms. You can have molecular crystals, or you can have protein crystals. But mathematically, this is how you start describing how crystals. You have a specific lattice and you have a basis, which is the repeating unit. And it's mathematically an infinite array, infinitely repeating. If we think in 2 dimensions, and certainly there are 2D materials that are quantum materials, there's actually only 5 different arrangements you can make for a lattice. There are Bravais described all the lattices mathematically. So in 2 dimensions, there are 5 lattices you can make. There's the monoclinic, there's the orthorhombic, there's the hexagonal, and then there's the tetragonal. It's an interesting experiment to sit down and try to figure out if you can make another one. I did it just as a thought experiment for a while. But if you have the length, you have length A, length B, and some angle, that defines all of the monoclinic. If you make the angle 90 degrees, that's put certain restrictions. You have A and B and a certain angle. You can't arrange things and have a repeating unit beyond these 5 different ways. So we have 100 elements, and in 2Ds, we have 5 different ways to arrange them. It sounds like we're getting a little bit limited on what we can make, but not really. If we move to 3 dimensions, there are 14 Bravais lattices that you make: triclinic, monoclinic, hexagonal, tetragonal, orthorhombic, and cubic. So all the crystalline solids are one of these. All the 3-dimensional crystalline solids are one of these 14 lattices. They can have different basis sets. So they can have lots of different atoms or molecules occupying each of the coordinate sites, but it's one of these 14 lattices. As an example, here's the diamond cubic structure. It's a fairly important structure. It's the structure of silicon. So all your silicon, germanium, classic semiconductor devices are in this structure. And diamond, which is one of the quantum materials that you see at CIQM fairly often, is also this structure. So as the model rotates, does anyone have an idea of what the basis and what the lattice for this diamond cubic structure is? You can go ahead and unmute yourself if you want to speak up. No, if no one wants to take a guess. All right. Since everyone's being shy, I'll give you the answer. It's a face-centered cubic lattice, and then the basis is actually two tetrahedrally bonded atoms. So the face-centered cubic, let me go back. The face-centered cubic has an atom at each corner and has a site at each corner and a site in the middle. And for the diamond cubic structure, it has two carbon atoms. Well, in diamond, it has two carbon atoms. In silicon, it's two silicon atoms at each of these sites. And that's how you end up with this structure. So here's the face atom, and then there's the second atom. Here's the face atom. Oops, there's the second atom. It's easier to sit with a cup of coffee and think about it a little more. But it is a face-centered cubic lattice, and the basis is two atoms. While we're talking about silicon and the diamond cubic structure, I want to bring in this idea of Miller indices. So the Miller indices is how we describe the cut in a crystal. So now we have a crystal and we can cut it different ways. And if we take that silicon or diamond, that diamond cubic structure, and we cut it what's called the 110 face, here we have our lattice cube, and the 110 face would be this face over here. We see a certain pattern on that face. If we cut it on the 110, which would be sort of diagonally through our lattice cube, we get a different pattern. So this is interesting because the different faces are going to have very different electronic properties than we can already compare to each other. So silicon 110, silicon 100, silicon 111 are the three common silicon cuts. The silicon 111 is down here. It's sort of diagonally with the corner rather than diagonally in the face. And we see three very different arrangements of atoms. So our nuclear cores are differently spaced and differently arranged from each other. Our sea of electrons are going to see a different array of periodically positively charged things. And we're going to end up with different etching rates for the different silicon crystals. We're going to see difference in conductance across the different directions, things like that. So understanding the crystals and the crystal faces and the orientation, it changes the properties of the materials in a significant way. And we need to sort of think about it and be aware of it, especially when we're trying to design new materials or optimize electronic properties of a material, or even when we get up to devices, we want to be aware of the crystal structure and the orientation of the crystal structure, because these are all the same crystal, but the orientation of the atoms relative to each other is different. And by that difference, you get different properties. All right. So that was all a nice mathematical presentation. You can work out the math, and there's 14 Bravais lattices in 3D. How do we actually know experimentally that the solids can really be arranged as these crystals? So we'll go into experimental techniques next week, but briefly we can do X-ray diffraction. So we can shine X-rays onto a material, and the crystal lattice structure will actually diffract it. We'll go into next week what that means. But here's an X-ray diffraction from the Curiosity rover on Mars. So It even works on Mars. On Mars, they have crystals too, and we have the X-ray diffraction to prove it. We can have electrons diffract off crystal structures. So transmission electron microscopy, you can have the electrons diffract and give you specific patterns. We'll go into that next week, but it is weird to think about electrons having wave functions and that you can get diffractions when it has a mass. It needs to either go here or there, but it goes both places at once. But we'll go into that next week. And then there's also scanning tunneling microscopy, which lets you image basically the electron density. And here is the lattice of graphene. And if you stare at it closely, you can see what the 2D pattern is. I went ahead and penciled in the hexagonal crystal structure to make it a little clearer. Why do we care about the crystal structure and orientation? So I said that you get different properties depending on the crystal structure and the orientation. A very dramatic example for quantum materials is this twisted graphene that was discovered a couple of years ago. So graphene has these little hexagonal patterns. So graphene would be a single layer of carbon. It makes these small honeycomb patterns. But if you take two sheets of graphene and you stack them on top of each other, you get moire fringes, which are these larger hexagonal patterns you see. The moire fringes are interference patterns between the two layers of graphene. And the spacing of the moire patterns depends on the twist angle, how offset the two layers of graphene are. So if the two graphene layers are 1.1 degrees offset, you actually suddenly get superconductivity showing up. So you get this emergent phenomenon because of the crystal structure and the crystal orientation relative to each other and the overlap in those electronic orbitals. When they overlap in specific ways, you get new interesting quantum phenomenon occurring. So again, it's really important that we understand the crystal structures, we understand the orientation of the crystal structures relative to each other when we're putting together quantum materials. All right, so let's talk about crystals a little bit. So mathematically, crystals are this perfect, repeating, infinitely long structure, but nothing in life is perfect. So let's talk about the defects. The first big defect is the surface. The crystal has a surface. At some point it ends. It can't go on forever. The atoms in the middle are happy. They see the same environment everywhere they look. The atoms at the surface, they see something very different when they look up from when they look down. So they're in a different environment, and they're often, well, they are a much higher energetic state because they have dangling bonds. You often get surface rearrangement as it tries to minimize the free energy of the system. So surface energy is something important to think about. And the surfaces are defects in the crystals, especially as we go to smaller and smaller objects, smaller and smaller samples. The surface area plays a larger and larger role. And a very pretty example of this surface free energy is if you try to blow a soap bubble, or if you have a drop of water, it always ends up curved. And the curvature is trying to reduce that surface free energy. It doesn't matter if you blow the bubble out of a square bubble wand, it always ends up circular because that's the lowest surface free energy the system can make. Another effect of the surface atoms is surface adsorption. Because those atoms have this extra energy they're trying to reduce, they have these dangling bonds, they tend to grab things out of the air and adsorb them onto the surface quite easily. So this is often why for quantum materials we're trying to work really clean, we're trying to work in ultra high vacuum sometimes, to minimize this surface adsorption. And the surface adsorption is a phenomenon due to the higher surface energy due to this defect in the crystal. We can also have defects at interfaces. So here we have two different materials where it's stacking together, and they have different lattice parameters. The lattice parameter is the spacing between the atoms. So the yellow atoms have a slightly larger lattice parameter than the blue atoms. So we can see there's a little bit of offset between them as they try to line up. So that's going to distort some bonds. It's going to change the electrical and properties at that interface. So often we're trying to engineer the interfaces so that we get the properties that we want at the interface. So this would be semi-epitaxial growth. It means the crystal, the two crystals line up close, not perfect, but close. Perfect epitaxial growth would be if they happen to have the same lattice parameter, and then the crystal can just propagate. Even if you change the material, you could change the basis, but still have the same lattice structure and same lattice constants. And then that would be perfect epitaxial growth. So interfaces are another defect in the crystals. Often materials are polycrystalline. So here we have a bunch of crystals, and they're all oriented a little bit randomly to each other. And so then we have material scientists refer to as the different crystals as grains. So at the grain boundaries, at the interface between the different crystallites, we get lots of defects. So certainly lots of effort goes into either growing single crystal material. So the semiconductor industry has worked really hard for many years to make beautiful single crystal raw material. A silicon boule is like a 4-foot single crystal. Every atom is exactly where it should be. There's no polycrystallinity to it, because these grain boundaries are going to change the conduction. They're going to change the electrical properties. They're going to change the mechanical properties. If we imagine an electron being conducted along this row of atoms, and then suddenly it has to change its momentum a little bit to go along this row, and then it gets here, and then it sort of has to figure out how to hop and then go along this row. These grain boundaries are going to add resistance. They're going to, which is going to add heat to the system. The grain boundaries can be sites for other defects. They can be recombination sites. People engineer grain boundaries, passivate grain boundaries, try to make single crystal materials. It's something to be aware of. You know, even if you have a crystalline material, is it single crystal, is it polycrystalline? What are the size of the crystals? What's going on at the grain boundaries of the material? An interesting example, an interesting phenomenon when you have polycrystalline material is what's known as Ostwald ripening. So I said every time you make a surface, you have an energetic cost. If you have small crystallites and bigger crystallites, the energetic cost for the small crystallites is higher than the big crystallites. So the system can reduce its overall energy by absorbing the small crystallites into the big crystallites. So if you make some bubbles at home and you watch carefully, I meant to make a movie, but I ran out of time. It's usually the small bubbles will be absorbed by the big bubble, and the big bubbles will keep growing, cannibalizing the smaller bubbles until eventually everything pops in the bubble example. But even in solid materials, if you start heating them up and you have a polycrystalline phase with different size crystallites, the small ones will be absorbed into the big ones. So this is a phenomenon called Ostwald ripening, and you can make a nice home demonstration of it if you want to think a little bit more about surface free energy and polycrystalline materials and things like that. All right, some other defects in the crystals. We could simply be missing an atom. So missing an atom would be called a vacancy. We could have a different atom pop in into the wrong spot. So this would be called a substitution. we could have a smaller atom slipping in and hiding in the gap in the crystal structure. That would be called an interstitial substitution. And now if we pretend the blue circles are carbon and the red circles are nitrogen, and we put in a nitrogen substitution and have a vacancy next to it. This is called a nitrogen vacancy, or NV center in diamonds, which is one of the materials that's proposed to be used for qubits, for quantum bits, for quantum computing. And so it's really focusing on using defects and using the defects in the crystal in a controlled way. This nitrogen vacancy pair happens to give us an unpaired spin that we can control optically, which is a good way to manipulate the spins. But we've worked so hard to get a beautiful single crystal, and now we're purposely going through and ruining it, but ruining it in a controlled way. So putting in defects on purpose is called doping. So dopants have been used in the semiconductor industry for a long time, and they're defects that are done on purpose. So controlling the defects allows us to further engineer a material's property. So here's, again, a cartoon of silicon, and the black dots are the electrons surrounding the atomic cores. If we substitute a phosphorus in for one of the silicon atoms, then we have an extra electron. And so we have an extra electron here. And so this is called N-type doping because we have extra electrons. The electrons carry negative charge. So it's N-type. If we put in a boron atom where a silicon should be, boron has one fewer electrons. So we have a hole here. We are missing an electron. This effectively ends up having a positive charge. So we call it P-type. This hole can jump around. So you could think of the electron jumping here, or you could think of the hole jumping there and the electron jumping there, and then the hole can sort of jump around. It's like one of those kid puzzles where you have little blocks sliding around, and then there's one block missing, and you can try to move it around to make the puzzle work. So electrical engineers and physicists think of holes as their own set of particles, which is positively charged and can move. It's the absence of an electron. You can think of it if you have a bottle of sparkling water, the bubbles are going to move up, and the bubbles are really the absence of water, but we call them their own particle with their own physical properties. We call them bubbles, and the bubbles go up rather than stones going down. So holes initially are a little hard to wrap your head around, but just think of them as bubbles. Bubbles as in the absence of electrons, and the bubbles rise and the electrons sink. And so then you can accept that the holes are its own particle that's positively charged and can move around. All right, so we've talked about atoms and a little bit about how we put electrons in. We've talked about the nuclear cores and how we assemble them into 3D space-filling materials. And so let's dive into the quantum mechanical sort of heavier math side and go from wave functions to band gaps in materials. All right, so the wave equation for any free electron can be written as the time-independent Schrödinger equation. The Schrödinger equation is really just the kinetic energy plus the potential energy equals the total energy. The solution to the wave equation in one dimension is going to be A1 cosine kx plus A2 sine kx, where x is the spatial dimension. It's the real physical where it's moving to, and k is what's called the wave vector. You can think of it as a momentum dimension. So by substituting and rearranging things, we can determine that k, the wave vector, is the square root of 2me over h bar squared. And here's my little cartoon of a free electron doing whatever it feels like. And when we a little more rearranging, we find that the energy of the free electron is h bar squared k squared over 2m, which basically ends up as a nice parabolic curve, as you would remember from algebra 2. This makes a parabola. So if we plot it in energy versus k, which is momentum space, so energy versus momentum, we have a nice beautiful parabola. The electron can take any energy that it feels like within this space. But of course, having an isolated electron is a little hard to do. So in fields, of course, we have those positively charged ions that, those positively charged nuclear cores sitting around. But we'll model it with just a single nuclear core at the moment. And so if we put the electron in a potential well, so we restrain where the electron can go, and we model it as we have infinite sides to this well, and here's our potential energy, and our electron's stuck in the potential energy well, and we can go from minus A to A as the width of our potential energy well. We apply the boundary conditions and we can solve it, which ends up being Ka is equal to n pi. So we end up with discrete energy levels. N equals 1 is a half oscillation, n equals 2 is a full oscillation, the wave function n equals 3 is 1.5. And so there are discrete energy levels where it's allowed and some regions where it's not allowed. So with the bound electrons, we go from this free electron where it can have energy on this parabolic curve. So it's only allowed these discrete energies. And now if we expand this to a periodic potential, so now we have a one-dimensional atomic wire. The crystal atomic cores will provide these specific boundary conditions, and the electrons will be in these little potential wells in between them. And then there is some region in energy space where the electron can get out and be quasi-free and move along. So this would be conducting in a metal, but even in a metal, there are going to be some electrons that are bound to the nuclear cores. So what does this do to our wave function as we build up closer to a real material? Well, the periodic boundary conditions ends up deforming that free electron parabola, and the electron wave functions end up being reflected at certain zone boundaries. And so these zone boundaries are called the Brillouin zones. We can go from this representation and just fold these sides back into the first Brillouin zone, and then we end up with a representation like this. And we end up with the interpretation that there are forbidden energy regions where the electron can't exist, and then there's a band of energies where it's allowed, forbidden, allowed, forbidden, allowed. So now we have discrete energy levels. And so these discrete energy levels give rise to this quantized energy states. But of course, this is for a beautiful one dimensions. And in a real material, we don't have a single line of atoms. We have this much more complicated three-dimensional structure of the silicon atom. So here's the band structure of the silicon. The valence band, the allowed region, is this set of curves down at the bottom. There's a band gap in the middle, which is the forbidden energy region. The electron can never be in this energy region. And then there's the conduction band at the top. And the conduction band is those quasi-free states where the electron can move around and it's no longer bound to one of the atomic cores. So in the valence band, you can think of it as in one of those bound states to an atomic core. In the valence band, and the conduction band, it's quasi-free and can be conducted off to do useful things for us. And the band gap is this forbidden region. The electron can never be in that region. And of course, this representation of the band structure of silicons in 2 dimensions, but the silicon structure is in 3 dimensions. So it should really be a more complicated surface. It gets very hard to think in these 3-dimensional spaces. So that's why we usually use this 2-dimensional space, which is unfolded, sort of like a map is the unfolding of a globe. Here, this conduction band diagram is, this band diagram of silicon is like the map of this globe. So these letters down along the bottom are different crystal symmetries. So in 3 dimensions, we see these different crystal symmetries labeled. And then we can go from the 3D Brillouin zones of the FCC, and we can put in our Fermi levels. So this is where the electrons are actually going to be populated at 0 in 3 dimensions. So we can see that the electron distribution is not perfectly even. And again, we want to be aware of how the electron cloud and how the crystal is oriented, because that will change our conduction and material properties depending on how we orient the crystal sample. All right, so a couple more terms, a phonon. I'll talk next week sort of about why everything's a particle and a wave, the wave-particle duality, but for now, I'm just gonna say wave-particle duality is a thing in quantum physics, and a phonon would be the particle picture of a lattice vibration. So if we think of these red dots as the atomic cores and the bonds we're going to model very classically as springs, we can have different vibrations in between them, and they'll have certain resonant frequencies. And these resonant frequencies are going to end up giving us discrete quantized energies. And if you're having trouble going from sort of this wave picture, all right, so we have waves going along our, think of it as a slinky if you want. Try to follow one of these compressions and you can see how it moves along. And so again, you can model that as the particle. And so the particle moves along and it's really the compression that's moving along. So we're gonna model lattice vibrations also has a particle, which we call a phonon. And then we're gonna go back and look at the band structure one more time. And we're gonna think about, we still have the laws of conservation of energy and laws of conservation of momentum. So if we have an electron at the top of the valence band, we want to move it up to the conduction band so we can do something useful with it. If we just do a vertical transition, we need a change in energy, but we don't need any change in momentum. So we need energy to come into the system that can come in the form of a photon, it can come in electrically, it can come in as heat. But somehow we need to bring energy into the system, and then we can excite the electron from the valence band up to the conduction band. But that vertical transition doesn't take it to the lowest position in the conduction band. The lowest energetic position is actually over here on the conduction band. But to transition the electron from here to there, we need a change in energy and a change in momentum. And so to account for that conservation of momentum, we need to couple into a phonon, which is why I introduced the idea of phonons at this point. So we can couple into energy and momentum, and then we can transition diagonally along this band diagram. So we can still have conservation of energy and conservation of momentum hold. So that would be for transitions up. When in these cartoons, I drew transitions down, but there's sort of 2 classes of semiconductors. We can call them direct bandgap and indirect bandgap semiconductors. So in a direct bandgap semiconductor, the bottom of the conduction band, the lowest point of the conduction band is directly above the highest point of the valence band. And so then you only need a change in energy. So here, a photon is coming out as the electron transitions back down from the conduction band, from the bottom of the conduction band to the top of the valence band. And so examples of direct bandgap semiconductors would be gallium arsenide or zinc oxide, those sorts of materials. Silicon, as I pointed out, is already indirect bandgap. So the lowest point of the conduction band is offset in momentum space from the highest point of the valence band. So to get a photon coming out, we also need to couple into a phonon at the same time to preserve momentum. So we need to preserve energy and preserve momentum. Because you have to have multiple things coupling in at the same time, this is a much less probable event to occur. And so this is why emission from a silicon is so weak. So just when you're looking at transitions up and down, the direct bandgap semiconductors are going to be much more likely to have those transitions. The indirect semiconductors, silicon, germanium, you need to couple into a phonon, and so those transitions occur, but they're much, much less likely to occur. All right, so let's talk a little bit about where we've gotten to. So we're trying to work up to building some sort of new quantum device. And the basic materials, the basic building blocks for making a device are metals. So we want to be able to conduct electricity where we want to go, where we want it to go. And in metals, there's no band gap. The conduction band and valence band overlap each other. And so the electrons are free to flow. There's always some electrons that are free to go whenever an electric field is applied. Semiconductors have a band gap, sort of a medium band gap. You can engineer the band gap in different ways. Different materials will have different size band gaps. But the point with the band gap is we can turn it on to be a conductor when we want it to, and we can turn it off to be an insulator when we don't want it to conduct electricity. So this semiconductor material lets us turn on and off whether it's a conductor. And that's really key to making a useful device, is being able to control when the electrons are flowing and when they're not flowing. And finally, we want some insulators. So we want to be able to block electrons from flowing wherever we don't want them to flow. And so in your normal household wire, it's a polymer plastic coating on the outside of the wires to keep the electricity from going where it shouldn't go. And basically, to have an insulator, you need a wide band gap material. When we're making devices out of 2D materials, the metals are still predominantly metals. The semiconductors are often like the transition metal dicalcinides, the TMDs, MOS2, for example. And then the insulators are usually like boron nitride. Boron nitride has a really wide band gap. So these are our three building blocks that we want to sort of be able to engineer and put together into making devices. If we go back and talk about how doping affects the energy levels. So we had the picture of the dopants in a semiconductor. If we go back to our valence band, conduction band picture, an N-typed material will have an extra electron energy levels, which are usually inside the band gap. And it pulls that Fermi level out of the conduction band. In a P-type, there's an extra level of whole energy levels, and it pulls the Fermi level up. And so if we take the N and the P-type materials and we put them together, we get an interface. And then at that interface, we end up with sort of an energetic slide. So the vertical is energy space, and then the electron will go along, but then it'll see a lower energy level so it can go down the slide and go this way. The holes flow in the opposite direction. You can think of them as the bubbles. They're sort of bubbling up and going this way. And now the electrons in the holes are much better behaved than my kids. My kids love running up the slide at the playground, no matter how many times you tell them not to. The electrons in the holes will only go down the electrons will only go down the slide, the holes will only go up the slide. So now we have a one-way switch. The electricity will only flow the way we want, and this is called a diode. If we engineer things a little bit so that we have a nice direct band gap and we can get a photon coming out when the electrons and the holes recombine here, and it emits a photon. The photon, we've now made a light emitting diode. So the electrons come and then they recombine with the holes. Conservation of energy says the energy has to go somewhere. The energy goes into the creation of a photon. Photons are nice in that they have no mass. So we can create and destroy photons sort of at will, but they do carry away energy or provide energy. So photons, you don't have to worry about conservation of mass, but you do worry about conservation of energy, and we're taking the extra energy from the electron and holes recombining and getting photons. And by tuning this band gap, different size band gaps will give us different colors of LEDs. So the blue color, that a blue photon contains more energy than a red photon. So a blue LED has a wider band gap than a red LED. And then if we add some mirrors, these are usually in a semiconductor, just the facets on the end of the crystal are cut so that they're reflective. We make a resonant cavity, and then as the photons are generated, they bounce back and forth between the resonant cavity and generate a laser as the output. The laser output in a laser diode is how your normal laser pointer works. So now we're up to generating a useful laser diode using our building blocks. And the laser itself is a nice demonstration of bosons behaving differently than fermions. All right, so hopefully that was a reasonable introduction to sort of the ideas and techniques on engineering new quantum materials. So we want to control the electronic band structure, and we want to control it in ways usually using defect engineering, so that we have some things that are conductive, some things that are semiconducting, and some things that are insulating, and then we can put them together to be a full device. So here is the Brillouin zones of graphene. So hopefully this funny shape now makes a little more sense to people what exactly it's showing. It's showing energy versus momentum space. And at certain points, we get what's called a Dirac cone, where the valence band just touches the conduction band. So there is no band gap in graphene, and lots of people are trying to engineer a way with dopants to open up a little bit of band gap so you can make graphene into a semiconductor and then start making devices. So with that, I'll wrap up for this week. So in summary, quantum materials, we're going to think of them as mainly crystalline solids, and we need to understand the crystal structure of the material because that affects its electrical properties strongly. And we want to control the defects. We don't want there to be defects that we aren't expecting, and we do want to be able to put in specific defects at specific sites so we can engineer the band gap and the conductivity of the material the way we want. So for this talk, I went back to my undergraduate textbooks, the Elements of Materials Science and Engineering, the Electronic Properties of Materials, and Introduction to Physics in Electrons of Solids. All these texts were present this material in a very accessible way if anyone wants to pick those up and read them. I did check online. They're all available used for like $5 or $6, which makes me sad because I spent hundreds of dollars on them when I was an undergrad. But anyway, life moves on. With that, I am happy to take any questions that people have, and I look forward to seeing everyone next week when we dig into some of the experimental results that prompted all this understanding.
Thank you so much, Arthur. This was great. I'm going to leave the questions for students. We have one chat. Carolyn said this was a great introduction. Are there any questions? So Arthur, how would you feel if and there are no questions in the chat.
Everybody's too shy.
I think everyone's too shy. So we can have people, if you want to send in questions through the Google Drive or something like that.
Yeah, I'm happy to ask questions, answer questions, however people are comfortable. You can email me. We can set up a time to chat one-on-one on the phone or by Zoom or whatever people are comfortable with. But I'm happy to discuss all these topics in greater details. This was supposed to be sort of the overview level, and then we can dig into the details one-on-one as people are interested.
I know I'll spend some time to go back and for some of the things that I may not recall. I think everyone would benefit from doing that. But I find it a very good introduction to get people in the space of what they need to be thinking about. So.
I actually have a quick question.
Yeah, go ahead.
Okay, firstly, thank you so much for the lecture. It was very interesting. So my question was about the p-n junction, and I was just wondering why from the p-type to the n-type, the electrons and holes are like sliding up and down rather than like going vertically downwards and upwards. Yeah.
Right. So it's a cartoon, so I stretched it out a little bit, but basically the idea is you can't have discontinuity in nature. There can't be the instantaneous drop from this state to that state because you'd have a physical position where you have two measurable values that are for the same physical position. So you end up bending the bands across a certain space rather than it being an instantaneous drop. Okay. It just, nature does not like discontinuities. You can't have it both at the same space in the same position in real space. You can't have a value of 10 and a value of 1 at the same position. You have two answers for the same spot, and it just doesn't work in real life. So in real life, you end up bending across a certain region rather than having an instantaneous drop. It's a smaller drop than I've drawn here. I exaggerated it in the cartoon, but it is not zero.
Okay.
Does that help?
Yeah, thank you.
All right. Any other questions?
The slides were great, by the way. I really appreciate the time you put in.
Oh, thank you.
They're really awesome. Yeah. Oh, so you know what? I'm going to stop recording.
Okay.
That way, just in case people have questions, and maybe they don't want to record it.